Hi everybody. Today in class you're going to be working on the unwinding string problem. This is a prelude to a lab we're going to be doing later on using real apparatus. The idea here is to be able to eventually calculate the rotational inertia for an unknown object based on its motion. So in this situation we're going to have a hanging mass pulling on a disc or a bicycle wheel. The following video kind of illustrates that situation. So here we can see that there's a hanging mass along the edge of the disc. When the string is cut, the mass is going to fall, and then that falling mass is going to cause the disc to rotate. Then of course once the disc stops falling, the mass stops falling, the disc has constant velocity. So if we look at this, it kind of reinforces what we've already talked about. You can see that the string is attached to the disc and we have a lever arm distance, and the force of the mass falling pulls a string which will create a torque. Since there's only one force acting on the disc, that force times the lever arm is going to cause a net torque. And since we have a net torque, the disc is going to not be in equilibrium, and so it's going to have a rotational acceleration. So the force needed to find the torque is not the weight of the falling mass, as you might think. It's the tension in the string. And the tension in the string and the weight of the falling mass are not equal in this case. And the reason we know that is because the mass accelerates down. So since the mass accelerates down, there must be a net force on that mass. And as we talked about earlier this year, because the weight and the tension are acting in opposite directions, that net force is going to be mg minus the tension. So according to Newton's second law, F net is going to be equal to the mass times the acceleration. And again, we're talking about the net force on the hanging mass, not the wheel at this point. So rearranging that to find for tension, we have mg minus tension equals ma. Tension is going to be equal to mg minus ma, and that means that tension is going to be equal to m, which is the mass of the block, times g, the acceleration due to gravity, 9.8, minus the acceleration of the block. And so we're always talking about the acceleration of the block here. Now, in order to solve this, we need to know what the acceleration of the block is. And so in today's activity, you're going to know what that is. You're going to be given that acceleration. Otherwise, there has to be some other way of finding it. So since the mass and the disc are connected to each other, they must have the same linear acceleration. And that's very, very important because we know the values for the hanging mass, but now we need to find the acceleration of the disc. And so this concept is crucial, that the acceleration of the hanging mass and the acceleration of the disc have to be the same. Now, what if we don't put the rope or the string on the outside of the disc or the wheel? What if the string, like in the activity we did the other day, is attached to the hub? Now, the definition of a hub is just simply a smaller cylinder or a smaller wheel attached to a bigger wheel. So because the wheel and the hub are connected and they're going to be rotating together, their rotational accelerations must be equal. But otherwise, everything's still the same. The string is wrapped around the hub, so when the string is pulled, it's going to provide a torque on the hub. And that torque is going to cause the wheel to have a rotational acceleration, and that rotational acceleration can be converted to a linear acceleration. The linear acceleration of the wheel is going to be the same as the linear acceleration of the falling block, and again the net force on the block is going to be mg minus tension. And so in order to find the torque on the hub, you need to find the tension, just like we did before. So as you're working on this activity today, you can go back and look at this video, but the activity is meant to be gone through a step at a time. Good luck, and we'll be going over it tomorrow in class.